So today we will discuss about the block 4. Is it visible to you and audible? So today we will discuss about the block 4. Am I audible? Am I audible? Do you hear me?
Yes, sir.
Okay. So today we are going to discuss block 4 analytical techniques in environmental chemistry. You know what is analytical techniques? Basically the instruments that we use for analysis of uh, uh, environmental pollutants. We will discuss about analytical techniques and its importance, classification of analytical techniques, chemical methods of analysis, electrical methods of analysis, optical methods of analysis, nuclear methods, thermal methods of analysis. Criteria for evaluation of analytical data are error and detection of error, how to and accuracy and precision, and then reporting of results, chemical expression of results, numerical expression of results, and significant figures. So these things we will discuss today. So what is the importance of analytical techniques? You know that an environmental analyst analyzes the type of chemicals and the amount of chemical present in the pollutant, or otherwise in the given sample. So basically, when an analyst analyzes a chemical sample or a water sample, he analyzes, or he or she analyzes the chemicals present as a pollutant and pollutants or given in the given sample. The constituents to be analyzed may be elements, ions, radicals, functional groups of a compound. So we can analyze what are the elemental analysis, like carbon, hydrogen, sulfur, or mercury, all those, whatever element is there. Ions, whether it is a cation or anion, or radical, free radical, or a functional group like a hydroxyl group or a amino group, or any kind of functional group. So there are many different analytical techniques available, and in the field of science like chemistry, physics, biology, biochemistry, and geology, even engineering, all those fields, there are many analytical techniques available to characterize a substance and get its functional groups or elements, ions, radicals, all those things, information on those. So so then, choosing a suitable technique, we have to first choose a suitable technique. The analyst has to keep in mind which technique is required for the analysis. So, and it depends upon what type of sample to be analyzed, information sought, purpose of the analysis, accuracy, sensitivity, and selectivity of the instrument. So what kind of analysis, what kind of sample we are going to analyze? We should get the information about uh, what information is actually required, then purpose of the analysis, accuracy, sensitivity, and selectivity. So then performance of analysis will depend upon the following: experience of the analyst. So if you don't have any experience in analysis and handling the instruments, then it's obviously difficult for you to do the analysis. Availability of the equipment, which what kind of equipment is available, depending upon that you have to choose the method. So different suppose a spectrometer photometer, UV visible spectrometer photometer can be utilized for analysis of various pollutants. If you have a spectrophotometer, you should choose a method suitable for uh, the UV visible spectrometer. Otherwise, if you don't have, then you have to follow other methods. Like if you have a sensor is there, you have to use the sensor for that. So preparation of the sample for analysis, time and cost involved. So how much time is required and what is the cost? Some analysis are very time consuming. Some analysis are very extremely lot of money is required for those analyses. So that means we should avoid those time consuming analysis and the analysis which has high cost. So then classification of techniques, we have chemical methods, electrical methods, optical methods, nuclear radiation methods, and thermal methods, separation methods. So all these are there. So classification of different analytical techniques, you see chemical methods, gravimetry, volumetry; electrical method, potentiometry, amperometry, voltammetry, coulometry, and conductometry, high frequency methods. Then optical methods, emission spectroscopy, absorption spectroscopy, UV visible spectroscopy, IR spectroscopy, fluorophotometry, turbidimetry, nephelometry, Raman spectroscopy. So then another are these nuclear radiation methods, the radiochemical methods, radiometric methods, isotopic dilution methods, activation analysis, Mossbur, nuclear magnetic resonance, and mass. Then thermal methods, TGA, thermogravimetric analysis, derivative thermogravimetry, DTG, differential thermal analysis, DTA, differential scanning colorimetry, DSC, thermal and thermometric enthalpy titration, TET. Then separation methods like chromatography, solvent extraction, ion exchange, electrophoresis. Chemical methods of analysis. Chemical methods of analysis belong to the board type of analysis called the quantitative analysis. As mentioned earlier, these methods are based on the measurement of quantity. In one case, it is the mass of the substance, while in other the volume is taken into consideration. The corresponding methods are known as gravimetry and volumetry. Both of these being developed at early stages and are known as classical methods of analysis. So what is a gravimetry? Gravimetry is an accurate macro analysis procedure by which procedure which mainly depends upon precipitation of ionic and molecular substances on the basis of chemical reaction. So basically gravimetry is basically based on precipitation. If something is precipitates out, you take the precipitates, filter it, and analyze what is the weight of the precipitate. So basically that is the gravimetric analysis. In gravimetric analysis, the component to be estimated is converted into an insoluble precipitate, which is filtered, dried, ignited, and weighted accurately. So basically that's the thing, you have to filter it, dry it, ignite it, and weight it accurately. Knowing the stoichiometry of the chemical reaction involved in the precipitation, the mass of the precipitate is used to determine the amount of component in the substance. At undergraduate level, you might have estimated barium sulfate. So in UG level, those who have chemistry background, they can remember the estimation of barium and as a barium sulfate. If you precipitate barium, you should make it a sulfate, and barium sulfate will precipitate as a white precipitate. Then you can separate it out by filtration and then drying it and find out how much barium is there in the solution. That volumetry. Volumetry is the amount of analyte can be determined by measurement of volume. So volume measurement, by volume measurement, you can measure the amount of analyte present in the sample. So in this method, in this method, volume of a of reagent solution of accurately known concentration is taken for a reaction known as volumetric analysis. The measurement of volume saves time to a considerable extent. The greater the speed of volumetric analysis is an important, the greater speed of volumetric analysis is an important advantage over gravimetry. Volumetry is more advantageous than gravimetry because gravimetry takes time because of precipitation, all those things. But this volumetry is a better method and more faster, less time consuming. So the volumetric analysis is characterized by titration. Volumetric analysis is characterized by titration. Hence, the method is also known as titrimetry. Volumetry can also, basically you do titration. Titration means take a titrant and measure the volume, then take a titrant and add an indicator. You add an indicator when you add at the end point, you get a change of color of the indicator. That means that your reaction is done over, and then you find out how much amount of titrant is used, and then from there you calculate the amount of your analyte present in the sample. So that's why you do volumetry. So next is electrical method of analysis. Electrical means potentiometry, potentiometric titration are there. So then amperometric titration is there. Voltammetry. In voltammetry, an electroactive species is consumed, oxidized, or reduced only at the surface layer of the indicator electrode in the electrolytic cell. The resulting current due to electron transfer process is measured as a function of applied potential. The current versus potential curves are plotted. In voltammetry, we study the relationship between the current and electrode potential and is applicable to chemical analysis. Coulometry is analytical method on the measurement of quantity of electricity are designated by the term coulometry. So the term derived from coulomb. Coulomb means which is the one unit of current, quantity of current fast. So a fundamental requirement of all coulometric methods is that species determined interacts with 100% current efficiency. Conductometry, in the measurement of conductance, can sometimes be useful in chemical analysis. Methods based on electrical conductance measurement are grouped under the term conductometry. The analysis can be computed directly from conductance measurement or by determination of equivalence point of titration or conductometric titration. Then optical method. In optical methods are called spectroscopic method. You know, spectroscopic method means when there is when the substance observes, analyte observes what electromagnetic radiation, then that is called spectroscopic method. It could be classified like emission, absorption, or scattering type, or type of EMR, X-ray, whatever the electromagnetic radiation. If you are taking X-ray, it is X-ray spectroscopy. If you are taking UV visible radiation or electromagnetic radiation, then it is UV visible. If you are using IR as electromagnetic radiation, it is called IR spectroscopy. The important spectroscopic methods are mentioned below. Emission spectroscopy. The method depends upon electromagnetic radiation produced when the analyte is excited by thermal, electrical, and radiant energy. Each element has a characteristic emission spectrum. This is applied to quantitative analysis. Quantitative determination are also possible. So then absorption spectroscopy. This method is based on measurement of the absorption of electromagnetic radiation by matter. Absorption refers to a process by which chemical species in a transparent medium selectively absorbs the photons of certain electromagnetic radiation. Then first, most important among the all spectroscopic methods in environmental analysis is UV visible spectroscopy. The analytical methods which involves measurement of absorption of ultraviolet or visible radiation. Wavelength range of the UV visible radiation is 180 to 780 nanometer by an atomic, ionic, or molecular species is known as UV visible spectroscopy method. UV and visible spectroscopy involve transition between electronic level of observing chemical species. These methods find application in qualitative as well as quantitative analysis. Next is IR absorption. IR absorption is infrared spectroscopy. Involves the absorption of IR radiation. IR radiation wavelength 0.78 to 1000 micrometer. Just after UV visible, there is a IR radiation. So then, depending upon increasing, so basically, what happens in IR radiation? The IR radiation in this there is a depending upon on increasing the energy of vibration or rotation associated with the covalent bond. So basically, there is a vibration due to absorption of IR infrared radiation. what happens? There is a vibration of change in the vibrational energy of the molecule, or it rotates the bond rotation, vibration of a covalent bond. So provided that such an increase results in change in the dipole moment of the molecule. If there is a change in the dipole moment during vibration and rotation of the molecule, then only that molecule will be IR active. If there will be no dipole moment change, then that molecule will not be IR active. So next is fluorophotometry. The energy of photons of incident radiation observed and changes the observing species to excited state. Certain chemical substances after excitation can re-emit radiation. Re-emission of radiation can be immediately or can be immediately with less than in less than it occurs less than 10 to the power minus 8 second after the absorption of the UV visible radiation known as fluorescence. If the re-emission of the radiation is very instantaneously occurs, means that time gap is less than 10 to the power minus 8 second. That is called fluorescence. The fluorescence intensity is practically proportional to the concentration of fluorescent substance. The measurement of intensity of fluorescence serves useful analytical purpose, and the technique is known as fluorophotometry. When re-emission of radiation takes longer time, the phenomenon is known as phosphorescence. So if the re-emission process, which is less than 10 to the power minus 8 second for fluorescence, if it is higher, more than that, 10 to the minus 8 second, that process is called as phosphorescence. Basically, fluorescence and phosphorescence are almost similar process. Only difference is the time reaction radiation time, or the re-emission of radiation time varies for both processes. Fluorescence instantaneous, and phosphorescence little bit longer. So then turbidimetry and nephelometry, analytical methods where determination are made by measuring opacity of suspension of small particles with the help of measuring intensity of transmitted light is known as turbidimetry. Then nephelometry is also the analytical method in which measurement of intensity of light scattered by a suspension of small particles is designated as nephelometry. So Raman spectroscopy is just opposite of IR spectroscopy. So here also, the when the electromagnetic radiation is applied and what happens, radiation is applied to a liquid or solution following Raman effect. Raman and they both, Raman and infrared spectroscopy techniques, they have the vibrational change. Both are vibrational change, and they are complementary to each other. So if a molecule doesn't have change in dipole moment, it will be Raman active. If the molecule has a change a change of dipole moment, it will be IR active. If the molecule doesn't have a change in the dipole moment, it will be Raman active. So basically, Raman spectra is based on change in the polarizability, and IR spectra is based on the change in dipole moment. So both are complementary to each other. If a molecule is not IR active, it would be Raman active. But if a molecule is Raman active, it will not be IR active. So they are basically same thing, same. They have the same basic fundamentals behind them. Only difference is they are complementary to each other. One is occurs due to changes in the dipole moment, other occurs due to changes in the polarizability. So next, nuclear methods. Nuclear methods, radiochemical methods, Mazur spectroscopy, nuclear magnetic resonance, and mass spectrometry. So these are. So radiochemical methods, radioactive disintegration of radioisotopes can be measured with a high sensitivity and specificity. Mazur spectroscopy, resonance fluorescence of gamma rays, and it is basically resonance fluorescence of gamma rays and involves intranuclear energy levels. NMR spectroscopy, interaction of quantized nuclear spin and an applied magnetic field. Mass spectrometry, mass to charge ratio of a ionized atom or molecule. So the mechanism involved are different in the thermal methods, TGA, DTG, TGA, DSE, TET, thermometric enthalpy titrations, So these methods have little bit different what principle, but they have the same temperature change. Most of them have they have the change in the temperature, and in thermometric enthalpy transition there is a volume change in the volume of the titrant. So separation methods, there are many separation methods: precipitation, distillation, sublimation, and modern chromatography, solvent extraction, ion exchange, electrophoresis. So these are all separation methods, different type. Chromatography, chromatography means is a multi-stage preparation process in which the sample is applied on a stationary phase over which a molecule mobile phase is percolated. Basically, there is a two stages: stationary phase over which a mobile phase is percolated. Various solutes present in the sample are separated on the basis of differential migration. Chromatography can be classified into various types depending upon the nature of stationary and mobile phases. It could be paper chromatography, thin layer chromatography, liquid chromatography, high performance liquid chromatography, gas chromatography, gel chromatography, partition chromatography, adsorption chromatography, ion exchange chromatography, and electro chromatography. There are so many types of chromatography based on just changes in the what? Based changes in the their stationary phase and mobile phase. Solvent extraction. In solvent extraction, a desired solute can be isolated, extracted by distributing it between two immiscible liquids. It exploits the differential solubility of given solute in two immiscible solvents. Ion exchange. Ion exchange is a stoichiometric process in which a solid material known as ion exchanger, when comes in contact with the electrolyte solution, takes either positive or negative ions and releases the ions of like charge to the like charge to the solution. So then the solid material having cation as exchangeable ions are known as cation exchangers, and having anions are exchangeable ions are known as anion exchanger. Ion exchangers exchange is a reversible process. The exchanged ions can be replaced by other ions of like charge. Ion exchangers find great utility in separating ionic species. So electrophoresis is a movement of charged particle in influence of electric field, in general known as electrophoresis. So basically, movement of charged particle under influence of electric field. If the components of a mixture have different velocities under the influence of the electric field, it is possible to separate them. This method has been used with remarkable success for separation and characterization of polysaccharides, nucleic acid, hemoglobin, and other high molecular weight compounds. Electrophoresis is useful for separation of high molecular compounds. So next is criteria of for evaluation. Analytical chemistry is enormous importance in science and university. It deals with the development of methods for chemical analysis, which are utilized in detection, determination, and separation of chemical constituents and structure elucidation of chemical compounds. So, in order to understand the criteria for evaluating the utility of analytical techniques, it is useful to identify the several steps in performing quantitative analysis. A complete analysis actually consists of the following: sampling, resolution of the sample, separation of interfering substances, measurement, interpretation of the measurement. So these are the analysis. The complete analysis of analysis consists of the following steps. So sampling, resolution of the sample, separation of interfering substances, measurement. So all these are there. So then next is evaluation of analytical data, error and detection of errors. First thing is, if we are doing an analytical use an instrument and do an analytical technique for analysis of your substance or pollutant, then there is a possibility of error in by the either by human being or by instrumental error or by sample preparation error. Different type of error is possible because it's a human being, we are working there. If we do a simple mistake there, that can lead to errors. So data obtained by the physical measurement should always raise the question of error in the nature. So basically, what is a error? the error is an inverse measure of the accuracy of the result. So that means less the error, more accurate is the result. Error is mathematically defined as the difference between observed value and the true value. E equal to error, which is equal to O minus T, O equal to observed value and T equal to true value. So true value, observed value, between two observed value and true value, the difference between them is called error. So for example, serial number 1, 2, 3, 4, 5. So your observed value is 249, but your true value is 249 milliliter, and our true value is 250 milliliter. So just difference between them is -1. So error is -1 ml. So same thing, if you are taking five readings, observations, for the same what same experiment. So out of the five experiments, you are getting different results, and then you subtract the true value from the errors in each five steps or five experiments you do, and finally you get how much total amount of error divided by number of steps is the 5. So that gives you average. So basically in an average you get -1 ml, -1 ml. So the error represented in the above table is the absolute error, and the average equal to error, average equal to error equal to total error divided by number of observations. So you have total error is -5 ml out in the 5 experiments, and number of observation is equal to 5. So then your error is -1 ml. So so that means more number of experiments you do, repetitions you do, you can avoid the error, and the error value will be less and less because you are taking average of those. So then, so if analyst see here, to understand the importance of relative error, let us consider a measurement of the capacities of three standard flasks, 10, 100 and 1000 milliliter, by three analysts, A, B and C respectively. So you see, true value equal to 10 ml, 100 ml and 1000 ml. Observed value we found 11 ml, 101 ml, 1001 ml. Error equal to 1 ml in each. So relative error E by T equal to 1 by 10 equal to 0.1. So 1 ml, and you are taking 10 ml is the true value. So relative error equal to 1 by 10 equal to this. So here also 1 ml and 1 by 100 equal to 0.01, which is relative error. E by T, E equal to the error divided by T equal to true value. So here you have 1 by 1000, which is equal to 0.001, is the relative error. So percentage of error equal to error error into 100 divided by T. So that means just relative error into 100 gives you the percentage of relative error. That means here 0.1 into 100. Sorry, no, that yes, multiplied by 100, that gives you 10%. Here 1%, and here 0.1%. So this is how you do the different types of errors. Uh, so in the error, the practical point of in the practical point of view, it is useful to classify error into two categories: determinate error and indeterminate error. What is determinate error? As the name implies, determinate error are those whose magnitude can be determined after assigning a definite cause, and thereby they are corrected for, and they can be corrected. Whereas indeterminate errors are the errors for those no exact cause can be assigned, hence they cannot be corrected. The sources of these errors may be similar to those for the determinate errors, but no definite causes out of these can be assigned for indeterminate errors. So determinate means which can be corrected. Indeterminates cannot be corrected. That is the difference between them. Sources of determinate errors which can be corrected: personal errors, operational errors, methodic errors. So then accuracy and precision. What is accuracy? What is precision? Accuracy. The term accuracy defined as the nearness of a measurement to its true value. That means more near the your observed value to the true value, more it is, more the accuracy basically. Or it is expressed in terms of error. Error defined already, error you know. So that means as you go closer to the true value, then your accuracy will increase. So that is called accuracy. And then precision. Precision is defined as the reproducibility of measurements. It tells an agreement between the numerical values of replicate measurements. The magnitude of random errors determines the precision of the analytical result. So precision is basically reproducibility. So that means how reproducible is your data. That means your data is precise, means more reproducible. So that means precision in a common way is expressed in terms of deviation. Deviation means how much it is deviating from the true value. So that is called deviation. So deviation or apparent error is defined as the difference between the measured value and the mean average of the series of measurements. So basically, you get the measured value and the mean or average of the series of the measurements is called as deviation or apparent error. So this is about precision and so see a, there are 5 6 data points are there inside the inner circle A. So if you're actually you should shooting, it is a shooting. So when a person is shooting to a target, or a athlete is shooting to a target, if most of his shots are within the inner circle, so that means that is the target. Inner circle is the target, and you are hitting inside the inner target, inner circle. That means that in that case the athlete is both accurate and precise because everything. So here B another athlete is there. He is hitting that, but outer, not the inner circle, but outer circle. But inner circle is the target. If you are hitting outer circle, that means it is not accurate, but it is precise because most of the shots is hitting outer circle. That means close to each other, very close to the outer circle. That means it is precise but not accurate. So but if you are someone is shooting, one is outer circle, one is nearby inner circle, one is completely outside the circles. So in that case, that athlete is not using a precise or a accurate shooting. They're not doing precise or accurate shooting. So this is how you can distinguish between accuracy and precision. So how to report the results? Analytical result is reported in two parts: chemical and numerical. Chemical expression means whether it is a what kind of element is present. Nitrogen is present, iron is present, calcium is present, chloride is present, or carbonate is present. So that is chemical expression. Numerical expression, it may be 1 ml, 5 ml, or all those. Or in the data, basically numerical values of 1 ml. So that is, so how if Wi is the amount of the constituent of interest, Ws is the amount of the sample, and C is a factor required to express the results in suitable units, the expression equal to Wi divided by Ws into C is useful for numerical expression of result of analysis. So this is, so then next is significant figures. In the preceding section, you learned how to report the results of measurements of an analysis. In this section, so what is significant figures? Significant figures means, so for, you see, a number is a mathematical expression of quantity. A figure or digit is any one of the characters 0, 1, 2, 3, 9. This is figure or digit, which alone or in combination serves to express the number. The digits of a number which are needed to express the precision of the measurement from which the number was derived are known as significant figures. What is significant figure? The digits of a number which are needed to express the precision of the measurement from which the number was derived are known as significant figures. So digits from 1 to 9 are always a part of the significant figures, while 0 may not be significant figure. A digit signifies the amount of the amount of the quantity in the place in which it stands. In case of the number 542, the number 542, the figure is figure signifies that there are 500, 410 and 10 units, and are therefore all significant. So 542 means it has all significance. The zero is used in two ways. It may be used in significant figure, or it may be used merely to locate the decimal place. When zero is the part of the measurement, it is significant. For example, the weight of a crucible is found to be 12.610 gram. The terminal zero is significant. That means the weight can be measured correctly up to third decimal place. The zero after one is significant because this is the part of the measurement. Similarly, expressing the concentration of a copper sulfate solution as 0.100 N. So the three zeros after one are all significant. Consider the number 107.2 centimeter. The zero between 1.1 and 7 are significant because both are placed between the two significant figures. This number has four significant figures regardless of where the decimal point is placed. So basically, so that means if you are talking about 0.001072 kilometer, all of them have significant figures. But where you don't have the significance. So next is how to do the rounding up. Rounding up means in rounding up quantities to desired number of significant figures by dropping the superfluous figures. So that means we can round up. Suppose you want to keep three digits. Okay, fourth digit you can round off. Okay, for example, so you see 3.55 is rounded up to two significant figures like 3.6. So see 3.5, then 5 is there. So if it is 5, then this has been rounded off to 3.6. 3.65 is rounded up to 3.6. Okay, and 65 is rounded up to 3.6. So 14.75 round up to 14.8. 2.652 is rounded up to 2.7. So if the dropped figure is less than 5, then the last retained figure is not changed. So basically, if we see, if the last the digit that you are going to omit or round off, if it is greater than or equal to 5, then the previous digit will change. One will be added to that. So see, 3.55 is there. If you are rounding up or you are taking away 5, then it becomes 3.6. Here 2.652 is there. So if you want to round off it to two significant figures, this 52 is gone. So you are converting it to 2.7. So So next unit is spectrometry. UV visual spectrometry, IR spectrometry, mass spectrometry. So little bit videos are there. What is the small videos I can show you on UV visible spectroscopy, spectrometry, IR and mass spectrometry, and its applications. So I can show you short videos. Okay, but the videos are seems lengthy, so it is not wise to show you the videos because it will take the time. But briefly I will discuss about these spectroscopy methods. You know, UV visible spectroscopy. UV visible spectroscopy, let us see about UV visible spectroscopy. Well, in UV visible spectroscopy, the electromagnetic spectrum that is used in this UV visible spectrometry is about 200 nanometer to 760 nanometer. Of these, the UV range extend from 200 to 380 nanometer, and visible range extend from 380 to 760 nanometer. So it's a UV and visible both. UV is 200 to 380 nanometer, and visible is 380 to 760 nanometer. So that means, so see, this is the electromagnetic radiation, and from um, in this you have UV. UV, far UV is 100 nanometer, medium UV around 200 nanometer, and near UV equal to 380 nanometer. So as you decrease the wavelength, like 100 nanometer, it becomes more and more energetic. So you see 100 nanometer has 1200 kilojoule per mole inverse, which is the energy. And in case of 380 nanometer, 315 kilojoule per mole is the energy. So gradually it also in UV, orange, red, gradually it increases. So that means it is also increase. Yeah, that means um, visible region has a lower energy than UV radiation. So because as the wavelength increases, energy associated with the EMR, electromagnetic radiation, is proportional, inversely proportional to its wavelength. So wavelength increases, energy decreases, wavelength increases. So when the molecule has, if the molecule has these electron, pi electron, sigma electrons are there, and they absorb energy from the UV visible radiation or electromagnetic radiation, they shift to the anti-bonding or more high energy orbitals. So that is called energy level diagram, and possible transition for a organic molecule. So these are the different types. N pi star, N is a lone pair of electron if it goes to pi star orbital, pi N sigma star orbital. So there are so many different type of transitions possible in an organic molecule when it absorbs UV or visible radiation, electromagnetic radiation. And you measure this is the cuvette in by which you take the analyte or the sample that you want to analyze, solubilize it, and keep that in cuvette and take it for UV analysis. So what happens when your analyte is inside this cuvette, and you are passing a incident radiation, and some of this incident radiation will be absorbed by the analyte inside this cuvette, and then after that that is absorbed, and I is after observance of this some of the initial radiation, the I which is the emitted radiation is I. So that means some of the incident radiation is absorbed by the analytes, and I is emitted, or emitted radiation is I. So there are difference. There is a difference. I zero is the incident radiation, whose value is different than the I, which is going out after passing through the analyte, through the cuvette. So that some of them is observed. So that absorbance leads to different pi star, n pi star, different type of transitions in the molecule, and you observe it like this. So then a band absorbance band is observed. So and then there is the difference between them is the width. So this is a fundamental. So how to quantify how much energy or how much incident radiation is observed. So that is basically governed by Beer Lambert's law. Beer-Lambert's law, what is that? When a monochromatic radiation of certain intensity is made to fall on an observing sample taken in a cuvette, a part of the radiation is reflected, another part is absorbed, and remaining part is transmitted. The decrease in the intensity of the incident radiation depends upon thickness of the observing medium as well as the concentration of the observing species. This dependence can be expressed in terms of Beer-Lambert law. So this law, in fact, combines the combination of two laws, basically Beer law and Lambert's law. So, so you just go through them. I don't have much time left. Already 1 hour is left. Almost 1 hour is left. So I have to show so many things. So you go through them. Beer law, and I just told about what is the definition of this Beer law and Lambert law. So next is basic instrumentation. You have a source, UV visible source. There is a monochromator. Monochromator means when your UV visible source light is there, it emits the lights of different wavelengths. But when the light passes through monochromator, it filters most of the wavelengths and passes only through the monochromator. Only single frequency or wavelength radiation is passed. So that is that is the role of monochromator. That means it filters other undesirable wavelengths, and only desired wavelength is passed through the monochromator. So there are two: one is a reference and one is sample, and then there is a detector is also there, and it detector detects. And you have processor, and there is a processor and the output. Output is basically a computer. Computer gives you the spectra, UV spectra, and there is a processor is there, maybe CPU, central processing unit of the computer acts as a processor. Okay, so environmental applications of UV visible: determination of heavy metals, identification of petroleum products in marine environment, determination of pesticides, determination of fluoride ion, determination of nitrate in water, determination of different organic compounds and surfactants like sodium dodecyl sulfates, and determination of ozone in ambient air by passing it into a solution of indigo disulfide sulfonate IDS. So these are. Next is IR. Only thing is difference is here IR spectra is used. IR radiation is used as electromagnetic radiation. When IR radiation passes through the substance or the analyte, it there is a change in the vibrational and vibrational energy. So you see there is a bond there, and then it stretches there. So you see, as there is a triple bond C, 2150 centimeter. Its vibration frequency is 2150 centimeter. When is a double bond reduced to 1650 centimeter, and is a single bond 1200 centimeter. So like this, as you the bond changes, or bond becomes single, and bond length changes. Yeah, its vibration frequency also changes. So that means for a different bond, you have to apply you will get a different vibrational frequency. So that means that's why a specific molecule always gives you a band at a specific position. That's why some of the regions of the IR spectrum is called as fingerprint regions. So that means a particular molecule will definitely give you a spectra like that, and you like your fingerprint, it doesn't change when you do your fingerprint. Like it doesn't change for a person. For a person to person, it is different. Same thing for a particular molecule, wherever you take the IR spectra, it will not change. So that's why IR spectra often acts as a fingerprint for a particular molecule, and you can identify that molecule by analyzing its spectra. So that has been already discussed in somewhere else here. See vibrational changes and vibrational ground level changes to how these two figures schematic energy level diagram for a vibrating diatomic molecule, how the changes in the vibrating energy. So origin of fundamental vibration. Fundamental means if there is a new 1 to 3 second overturn, new 1 to 2 there is a fundamental vibration, new 1 to 3 2 equal to fast overturn. So like this, different overtones and overtones and fundamental bands are observed in a IR spectrum. So you see there are different type of bending and stretching modes of vibration. One is asymmetric stretching. If the molecules are stretched asymmetrically away from each other, so that is asymmetric stretching. Symmetric, if they are stretched in a particular direction, a similar same direction, it is called asymmetric stretching. Bending, if two molecules they bend with each other, and then bending in and out of the plane of the paper. So basic instrumentation, so same thing, source is there is a reference and sample is there, and then there is a detector, processor and display. So this is the schematic diagram of this IR spectrometer. So environmental applications basically routine identification of and quantification of gaseous pollutants, sulfur dioxide, NO2, ammonia, ozone, measurement and monitoring of atmospheric gases, other and determination of volatile organic compounds, uh, waste management can be used for waste management, determination of soil organic matter, detection and identification of pollutant clouds in the atmosphere, determination of toxic and carcinogenic contaminants like chlorinated aliphatic hydrocarbons, chlorinated aromatic hydrocarbons. Then next is mass spectrometry. In mass spectrometry, you would recall the introduction and so what is the mass spectrometry? So here it is different. In mass spectrometry, we study the consequences of bombardment of species to be determined, uh, taken in a vapor phase with high energy electron beams. So high energy electron beams are bombarded with the analyte, okay, or the sample that you are taking for analysis. So that is called mass spectrometry. So this leads to ionization of the species by knocking off an electron from it. So basically molecular ion is generated and many other fragment ions are generated by the process of this bombardment of high energy electron beam with the molecule. Okay, so here you see methanol is there. Methanol you bombard with the electron beam, and one of the electron is knocked off. It's getting out, right, because of the high energy bombardment of energy electron beam. That gives you molecular ion for 2 electrons. So then molecular ion gives you then fragment ions, many fragment ions. So then that see, so this is the mass spectrum of methanol. 15 is the molecular weight of methanol molecule. So at sorry, 16 is CH3OH means 16 is the molecular weight of what methanol. CH3 no CH3OH is, the molecular weight is how much? She is 32. CH3OH 15, 16 plus 16, 32. So at 32 here, this is the molecular ion peak. So this is the molecular ion peak, and so many fragment ion peaks are also there. So the fragment ions represents the breaking of the methanol molecule inside the mass spectrometer and generation of different radical cations and anions. And the molecular ion, this 32 peak represents the molecular weight of the molecule, or like methanol in case of methanol 32 is the molecular weight. So you see here the same thing you have seen. The fragment ion, the peak, there is a small signal at 33. So 32 is actually molecular ion peak, and 33 equal to m plus 1 peak. If you may wondering where does this peak come from, the origin of this small peak is explained by taking natural abundance of isotopes of constituent atoms and molecules. So basically C12 and C13, there are two isotopes. C13 is there and C12 is there. So since there are two isotopes are there, for C12 isotope, which is the major isotope, you are getting a peak at here at 32, molecular m by z 32 is m by z. M by z is the molecular mass per charge ratio, and then y axis is the relative intensity. that is there. So then on 33 you see m plus 1 means that 1 is coming from the 13C isotope of the carbon, or carbon 13 isotope. That is the m plus 1 peak which is coming because of which is showing up there because of the presence of carbon 13. So instrumentation, like you have ion source, analyzer, detector, data processing unit, there is a vacuum setup there. So it's a schematic block diagram of mass spectrometer. GCMS is very useful in environmental analysis. Like previously in the previous classes, you might have heard about the GCMS for the pesticide determination. So pesticides and other chlorinated organic molecules can be detected very effectively by using GCMS. So this is the GCMS analyzer. So sorry, mass analyzer, where you have column, which is a gas chromatography column, chromatography column, and carrier gases are helium, nitrogen, and helium, nitrogen, and hydrogen, nitrogen, and helium. So there is a sample injector is there, and then after that, after separation of different components via this column, gas chromatography column, it passes through the ion source and then mass analyzer and detector. Here is it's a combination of two. GCMS means one is gas chromatography and then is mass spectrometry. The combined together are called GCMS. Environmental applications: detection of heavy metals like lead, mercury, determination of concentration of heavy metals like chromium in the soil water samples, characterization and quantization of quantitation of organic pesticides, evaluation of and fate of newly developed pesticides in the environment in terms of its transport properties. So all these. So next unit is about chromatography technique. There are many chromatography techniques are there, like gas liquid chromatography. Chromatography technique means separation techniques. When you want to separate one component from a mixture of components, then you have to use separating techniques. And chromatography techniques are modern separating techniques. It could be gas liquid chromatography, high performance liquid chromatography, supercritical fluid chromatography, so all these. So and then application of chromatography techniques in environmental monitoring. So are there. In the gas liquid chromatography, it's a technique employed for the separation of two phases in a mixture, where one is a stationary phase and the other is a mobile phase. Stationary phase is a non-volatile liquid coated on a liquid surface, and mobile phase is a carrier gas which is inert in nature, that is unreactive gas such as neon, helium, argon. The gas liquid chromatography is a type of partition chromatography. So I can show you this gas chromatography. Maybe this gas chromatography, I can show you a short video on this.
Here, one quick biochemistry basics here. Let's talk about gas chromatography. Gas chromatography is a chromatography
Is it audible to you? Visible?
Yes, sir.
So you see the figure.
technique used for the separation of volatile compounds. Volatile compounds are the compounds that gets easily vaporized at room temperature. Let's see the components of gas chromatography. The column. The column used in gas chromatography is very long and arranged in a coil. The column used in gas chromatography are of two types. Number 1, pack column, and number 2, capillary column. Pack column. Pack column can be made up of glass or stainless steel. The length of this column can vary from 1 to 3 meters and has an internal diameter of 2 to 4 millimeter. The capillary column. The capillary column is made up of fused quartz. These columns are very long and have length from 10 to 100 meters and have an internal diameter of 0.1 to 1 millimeter. The column is placed in a chamber so that a uniform temperature can be maintained. The stationary phase. The stationary phase is packed in the inner wall of the column. The stationary phase is made up of silicon grease or wax which can withstand a high temperature. The mobile phase. The mobile phase use is usually an inert gas like helium or unreactive gas such as nitrogen. The mobile phase gas is kept in a cylinder which is connected with the column via molecular sieve. The molecular sieve separates the unwanted hydrocarbons, oxygen and water vapor that may interfere with the test sample during analysis. At the end of the column, there is a detector which detects the sample. Let's see the working of gas chromatography. The sample which is to be separated is mixed with an appropriate volatile solvent such as heptane, acetone or methanol. Just before the column, there is a septum that allows injection of the sample. The temperature of the injection region is kept 20 to 50 degrees Celsius high as compared to the column. This allows rapid volatilization of the sample. Once the sample is volatilized, it passes down the column where the separation occurs. During analysis, the temperature of the column is kept between 150 to 300 degrees Celsius. Separation occurs based on the interaction of molecules between the mobile phase and the stationary phase. The less volatile molecules interact more with the stationary phase and move slowly, while the more volatile molecules interact more with the mobile phase and moves fast down the column. Once the separation is completed, the detection is done with a detector attached at the end of the column. One of the most common detectors used with gas chromatography is flame ionization detector or FID. The flame ionization detector has three inlets, one for the carrier gas which comes from the column and the other two for hydrogen and oxygen. The igniter ignites hydrogen and oxygen to produce a flame. When the sample molecules reaches the flame, they get ionized and the electrons are released. Across the flame there are two electrodes, each with a positive and a negative charge. The electrodes detect the electrons generated by the ionization of the sample. The electrons are detected in the form of current which is amplified and detected by the computer. When the sample is detected, the computer gives a peak with respect to the retention time of the sample. The area under the peak gives information about the concentration of the sample. If the concentration is less, the area under the peak will be less, and if the concentration is more, the area under the peak will be more. Now, for the detection of unknown samples, we need to have standards. Let's understand this with an example. Suppose we run methanol as our sample and the peak of methanol is obtained at 5 minutes. Next, we run acetone as our sample and the peak of acetone is obtained at 3 minutes. Next, we run unknown sample and we get this chromatogram. Now, using information from the standards, we can say methanol is present in the unknown sample, whereas acetone is absent. The remaining peak is still unknown as we do not have any standards to compare its retention time.
Okay, so we have a just brief idea on the GC gas chromatography. Then HPLC, high performance liquid chromatography. I will show you a short clip on high performance chromatography. Briefly, you can see high performance liquid chromatography.
In this animation, we are going to talk about instrumentation and working of HPLC. Full form of HPLC is High Performance Liquid Chromatography. HPLC instrument is constructed by compiling different parts, which are solvents reservoir, which contains different solvents, HPLC pump, degusser, which is attached with vacuum pump, solvent mixing valve, sample injector. Next part is pre-column, which is also known as guard column, and length of this column is 2 to 10 centimeters. Internal diameter is 4 to 5 millimeter, usually 4.6 millimeter. After guard column, next one is analytical column, and length of this analytical column is 10 to 30 centimeters. Again, internal diameter of these analytical column is 4 to 5 millimeters, usually 4.6 millimeter. The analytical columns and pre-columns are made up of stainless steel and filled with a stationary phase. Commonly used stationary phase is octadecylsilane silica gel, also known as ODS silica gel, and common names of these columns are C18 columns. Next part is detector, and finally coming to the recorder. Now let us discuss the working of these HPLC instrument. First, we will start the HPLC instrument. Then all parameters will be entered by the help of available HPLC software. And these parameters are solvent ratio, flow rate, runtime, type of elution, etc. After creating the method, solvent of the mobile phase will be pumped by the HPLC pump from the solvent reservoir towards the degusser. Now these solvents will come to the degusser, and degusser is attached with a vacuum pump which will create high vacuum. Therefore, any gas or air dissolved in the solvent will be removed online because this may create problem during elution. After degassing, solvents of the mobile phase will move towards the solvent mixing valve, and mixing of the solvents take place, which will help to produce uniform mobile phase. Now this mobile phase will run towards the pre-column or guard column. This guard column will remove any kind of impurity present in the mobile phase and protects analytical column from the impurities. In the next step, mobile phase will further move towards the analytical column, then finally goes to detector. In this condition, blank mobile phase will run for 10 minutes at least, which gives proper conditioning of the HPLC instrument. Now we will inject the required amount of sample through sample injector by the help of a micro syringe. After injecting the sample, it will pass through the guard column, then it will enter into the analytical column, which contains stationary phase. Due to the difference in the affinity with stationary phase, compounds present in the sample will be separated inside the column and reaches to the detector and gives signals in the detector. Compounds having least affinity with stationary phase will reach to the detector first, which is indicated by blue color. Then moderate affinity compound will reach to the detector, which is indicated by red color. And finally, highest affinity compound will reach to the detector at the end, which is indicated by green color. Ultimately, all signals will appear in the recorder. We have discussed the details about instrumentation and working of HPLC.
I hope you clearly understand the concept of HPLC. And as you have seen, we have done a lot of hard work to make this animation possible. So
Okay, next will be the videos is visible to you and audible. Videos are audible and visible or not?
Yes, sir.
Okay. So next, what is next? Next HPLC. Then after that, uh, so now it is visible to you.
Yes, sir.
So we will discuss now about the uh, separation techniques or chromatography techniques based on principle of separation. Adsorption chromatography. In this chromatography, the molecules of solute bond directly to the surface of the stationary phase. The efficiency of separation depends on solubility of the molecule in the mobile phase, binding strength to the stationary phase. So next is affinity chromatography. This is most selective chromatography technique that is based on specific reversible interaction between one kind of solute molecule need to be purified and the affinity ligand immobilized to the solid support. Next is ion exchange or HPLC. Ion exchange HPLC. In ion exchange chromatography that allows the separation of ions and polar molecules based on the charge they carry like like charges repel each other and unlike charges attract. Okay, so next is ion pair chromatography, gel permeation chromatography, chiral chromatography. So next, based on elution. Elution means what is eluted. Like one is mobile phase in chromatography. There is one mobile phase and the one is moving phase, and one is mobile phase and stationary phase. Depending upon the what kind of mobile phase you are taking, that also changes the different changes to different type of chromatography techniques. One is isocratic illusion, next is gradient illusion. Based on type of analysis, qualitative analysis, quantitative analysis. Applications of HPLC. HPLC is pharmaceutical application, environmental application, detection of phenolic compounds in drinking water, biomonitoring of air pollutants, applications in forensics, food and flavor, application in clinical tests. So all these. So next, disadvantages of HPLC: its cost is it is a costly and complex because it requires large quantities of expensive solvent, lack of ideal universal detector, lack of separation efficiency, all this relatively difficult for novices. That means if you do not have experience in handling HPLCs, you cannot run it. So next is supercritical fluid chromatography. Supercritical fluid chromatography was proposed in 1958 by Jim Lovelock. He suggested that polar components could be separated by using inorganic gases above their critical point as a chromatographic mobile phase, where mobile phase was considered to be inert carrier. So this is called supercritical chromatography. Supercritical fluid chromatography, this technique is highly compressed. In this technique, the highly compressed gases have been used. Above its critical temperature and pressure as mobile phase instead of organic solvent. In supercritical fluid chromatography, basically we use supercritical liquids as the mobile phase instead of normal organic solvent. Its principle is similar to those of high performance liquid chromatography, but supercritical fluid chromatography typically uses carbon dioxide as mobile phase. So supercritical carbon dioxide, which is a liquid carbon dioxide, is used as a moving phase, mobile phase. Then using the normal solvents, organic solvents. So that is supercritical fluid chromatography. Why carbon dioxide is used? It is easily available, has an accessible critical point, relatively safe, inexpensive, miscible with wide range of high polar modifiers, non-toxic in nature, non-flammable during reaction, dissolving dissolving power and selectivity can be controlled by selection of suitable pressure temperature combination. So, so this is about so what is the instrumentation of supercritical chromatography? Supercritical chromatography (SFC) instrument consists of a mobile phase container, which usually is a pressurized gas cylinder, mobile phase, a modifier, a pump, an injector, an oven, a column in thermostatic compartment, a microprocessor, and detector. So these are different components of a SFC or supercritical fluid chromatography. So next is application of chromatographic techniques in environmental monitoring. What are the applications? HPLC. What is the application of HPLC? HPLC helps to determine the presence of fluaginum in soil. What is fluaginum? It's a pesticide used against the fungal diseases in potato cultivation. A specific HPLC method is used that help to measure the presence of fluaginum in soil. A gas chromatography helps in measuring the ubiquitous pollutants in the environment. HPLC technique is used for analysis of air and water pollutants and for monitoring pesticide level in environment. Okay. Gas chromatography is used for determination of volatile organic compound VOCs in air. Volatile organic compounds are a cause of concern for human health due to their increased presence in the indoor environment. They are responsible for a phenomenon called as a sick building syndrome (SBS). Air monitoring method is used for assessing the indoor air pollution. So gas chromatography is most widely used for determination of trace organic compounds present in the environment. There are numerous gases found in industrial process and are harmful for plants and human beings, such as sulfur dioxide, hydrogen sulfide, so gas chromatography is used for the detection of these types of gases present in the air. Certain organic compounds such as carbohydrates and amino acids are identified or detected from a complex mixture of organic compounds with the help of vapor chromatography. It is used to separate anions and amino acids. Thin layer chromatography is used for determination of various plant extract. With thin layer chromatography, we also investigated the flavor components of the juices in citrus fruit. Column chromatography is used for identification and determination of non-volatile or strongly polar compounds in air and surface waste, and drinking waters. Size exclusion chromatography is used for removal of DOC, which is dissolved organic carbon from the drinking water. In size exclusion chromatography, a gel filtration based method is used for the purification of infectious rotavirus particles for environmental research application. Soil and water measurement contamination of soil and water measurement contamination of soil and water can come from many areas, including acid rain, pesticides, industrial waste, and raw sewage. Okay, GC have been used for differentiation of petroleum type pollutants and to study the fate of petroleum type pollutants in underground and surface waters. GCMS technique is used to study of the bioremediation potential of the microorganisms in crude oil biodegradation. So there are many different applications of the chromatography, very essential for environmental analysis. Am I audible?
Yes, sir.
The last unit is about radiochemical techniques. In radiochemical techniques, we have basic radiochemical isotopes, radioactive decay units to measure radioactive half-life, carbon dating, by radioactive labeling, pressure technique, isotope dilution, measurement of radiation. Uh, okay, so application of radiochemical techniques in environmental monitoring. Basic radiochemical technique isotopes. Iso means similar. Isotopes possesses different atomic weights with same atomic number of the same element. The chemical properties of these isotopes are identical. In other words, these isotopes own same number of protons and differ in the number of neutrons. Substances having natural isotopes need to be purified, and this is done in an atomic reactor or nuclear reactor. Unstable isotopes are known as radioisotopes. To obtain stability, they undergo radioactive decay. This phenomenon is commonly observed in elements like higher atomic number. Some of the commonly used radioisotopes are C12, C13, C14, C18. Okay, so isotopes used in field of biological studies, stable radioisotopes, and H2 is the stable. Okay, H3 is radioactive, H13 is stable, H14 is radioactive, N15 is stable, N18 is stable, N24 is radioactive. So what are the emissions that are coming? S3 beta emission, C14 beta emission, and sodium 24 with beta and gamma. It is half-life. Half-life means the amount of time required for decaying half of the amount of the radioactive compound. If you have 1 gram of a radioactive element of tritium H3, after 12.3 years it will be 0.5 gram. So that means half of it will be completely lost due to radioactivity. Okay, carbon 14, which has half life is 5730 years. Okay, it's long. So and sodium 24, whose half life is 15 hours, only 15 hours. That means if you are taking 1 gram of sodium 24 radioactive radioisotope, after 15 hours it will be 0.5 gram. Half of will be lost due to radioactivity. So radioactive decay, like lambda, an unstable isotope to obtain stability undergo ionization through emitting ionizing radiation. These ionizing radiations are in the form of alpha, beta, and gamma rays. So that is called radioactive decay, whether it's alpha, beta, or gamma. So alpha particle emission, uranium 92 238, uranium 238 gives thorium 90 234 with helium 42, which is alpha particle. Alpha particle has mass 4, charge 2. Okay, uranium is a alpha emitter. Alpha emitter. Gamma particle emitter. Gamma particle emission doesn't involve any mass change. Okay, so mass there will be no mass change. Like here, uranium converted to thorium. Same thing, a gamma particle emitter will not change its mass. measure of radioactivity, half life. Half life is a time required for the half of the nuclei in a radioactive sample to decay, represented by 0.5 divided by lambda. So becquerel, becquerel is BQ. The system international unit is used as becquerel as the unit of radioactivity. What is the unit of radioactivity? Becquerel. One BQ is equal to one disintegration per second. Previously, Marie Curie, Marie Curie, Madame Curie. So she was the discoverer of this radioactivity, and before Becquerel, Curie was used as a radioactive unit of radioactivity. Curie, Ci. This is the unit of measure, another measure of unit of radioactivity. Curie equivalent to the amount of radioactive activity to that of 1 gram of radium present in a given radioisotope. Basically, it is what equivalent to amount of radioactivity to that of 1 gram of radium present in a given radioisotope, which is equal to 2.22 into 10 to the power 12 disintegrations per minute. So these are units: millicurie, curie, and macrocurie. These are the different units of radioactivity. Others counts per minute, CPM, radiation absorbed, then disintegration per minute. So these are all different units of radioactivity. Important is carbon dating. Radiocarbon dating discovered by Willard Libby in 1946. He is a professor of chemistry, University of Chicago. So carbon dating was invented by Professor Wilbur Libby, which was a professor of chemistry at University of Chicago. For his discovery, he has been honored with Nobel Prize in 1960. So carbon dating is a very important method in radioactivity. So this method mainly based on measuring the level of radiocarbon for carbon 14 in a substance of or material. Radiation counting devices are used to perform carbon dating studies. Elemental carbon exists in both non-radioactive and radioactive atoms. Carbon has three isotopes: carbon 12, carbon 13, and carbon 14. Carbon 14 is radioactive, which is used for carbon dating. But carbon 12 and 13, they are non-radioactive; they are not used for any carbon dating process. Carbon dating mechanism. So you see here, following the death and burial of wood and bones and bones, following death and burial, wood and bones, they lose C14 as it changes to N14 by beta decay. Okay, so carbon 14 changes to nitrogen 14. So to measure nitrogen 14 in a particular so it is interesting to know that certain plants and animals can synthesize labeled compounds through their metabolic process when provided when provided 14C labeled nutrients. For example, Canna indica can produce labeled glucose, and pigeons can produce uric acid. So gradually uh, carbon 14 is converted to nitrogen 14. So from this we can calculate, from this data or the carbon dating data, we can find out how much of this carbon 14 has been converted to nitrogen 14, and from that data we can find out the age of the particular bone, or the age of particular wood, age of particular fossil. Fossil is basically when a creature dies, uh, the fossil is created. So that fossil is also can be, carbon dating of the fossil can be made to figure out the exact time period when that animal was 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 visible or was found in the earth. So that is called carbon dating. Next is radioactive labeling. Labeling means we can label radioactive molecules like DNA needed to incorporate phosphorus 32 into DNA double helix. So any radioactive labeling we can do, we can detect it anywhere in the body. If we label the molecule with a radioactive labeling, then we can detect that particular radioactive molecule or atom inside the body. So that is called radioactive labeling. In organic synthesis also we can label a C13 with C14. But C13 is non-radioactive, C12 is non-radioactive, C14 is radioactive. So we can also label a organic molecule with C14 carbon 14 nuclei or atom, so that is also help in organic synthesis to find its mechanism. Okay, biosynthesis tracer techniques are there. What is the application of tracer? Tracer is a, what is tracer? Tracer is basically technically so basically tracer is a disc tracer. Then isotope dilution. Till now we have studied about tracer technique. Now this is there is another method which is called isotope dilution. This method is used in quantifying the unknown concentration of a radioactive element in a sample by means of mass spectra photometer. So what is tracer? Tracer is basically discovery of tracer method for radioactive tracing took place in early 20th century. So technically, a tracer is an indicator that will help the researcher or investigator to track and follow the target. So basically, we can track, and if you add a radioactive atom to a particular molecule or a tracer, you can trace it where it goes, because there is a radioactive detector. If you put a radioactive detector, it will detect the presence of that particular radioactive nuclei or radioactive atom. So that is called tracer techniques. Isotope dilution technique similar to that. Measuring radioactivity. So how to measure radioactivity? It is assumed that any ideal instrument that can measure radioactivity would detect all type of radiation or radioisotope decay. But practically there is no such instrument. But the use separate detector or for each type of radiation. In the following section, there will be discussion about different type of instruments that are used for measuring radioactivity. So there is a Giger-Muller counter, GM counter. Okay, so GM counter is the one simplest device to measure the nuclear radiation, that is like alpha, beta, gamma rays. So sometimes the GM counter can be used to measure neutrons through alternative methods. So next is so all the details are also there. Then scintillation counter. Scintillation is the ability to emit the light after exposure to the external radiation or nuclear particle. Scintillation is the property of the material present inside the apparatus and is known to as scintillator. In this scintillation process, electrons move from high energy state to low energy state. During the process, they release light energy in the form of photons. So there is a scintillator counter, and then there is a GM counter, Geiger-Muller counter. There is a gamma counter. Gamma counter, what is it? Measuring gamma rays can be performed by using external scintillation detector. They are called gamma counters. Gamma ray counting the gamma ray emission of gamma particles, gamma rays. Neutron activation analysis, NAA. NAA was discovered 1936. So what is this? In this method, both qualitative and quantitative determination of element is possible. Very basic principle is working behind this technique is bombarding trace element with high flux of neutrons, followed by measuring the rate of decay or emitting radiation. Okay, so this is called neutron activity analysis. Applications of radioisotopes in environmental monitoring. climate change, ocean and seas, isotope hydrology, radioisotope ecology. So these are so different areas where you can apply the radioisotope uh, radioisotopes in environmental monitoring, climate change, ocean and seas, isotope hydrology, radioisotope ecology, all these. Okay, so we are done with all the 4 units, and we are also done with this environmental chemistry. We have gone through little bit of most of the portions, most of the all the portions of units of um, this environmental chemistry syllabus. Anything you want to ask? Anything you want to ask?
Sir, good evening, sir.
Yes.
Sir, radiative forcing ମାନେ କଣ sir?
Radiative
Forcing.
ରେଡିଏଟିଭ ଫୋର୍ସିଂ ହଉଛି ସେଟା ତମର ଯୋଉ କୋଉଥିରେ ହଉଥିଲା କହିଲ, କାଲି ଆମେ ଦେଖୁଥିଲେ ନା କୋଉଥିରେ
Glo-
ହଉଥିଲା କହିଲ?
global warming, sir.
ହଁ, ଗ୍ଲୋବାଲ ୱାର୍ମିଂ ରେ ରେଡିଏଟିଭ ଫୋର୍ସିଂ ମାନେ ଯୋଉ ଆମର ପର୍ଟିକୁଲାର ଯୋଉ ଆମାଉଣ୍ଟ ଅଫ ରେଡିଏସନ୍ସ ଦେ ଆର୍ ଆବଜର୍ଭ and certain radiations they are reflected back. Okay,
Sir,
say that is called radiative forcing.
sir, atom economy କଣ sir?
Atom economy means if you are taking that is in green chemistry. Okay, if you are taking 1 gram of the starting material or 1 mole of the starting material, if you get 1 mole of the product, the atom economic is 100%. That means none of the starting material is lost or degraded or converted to any other compound during the process of any or compound or byproduct during the process of your synthetic
ସେଟା
process.
100% ତ ହିଁ ବାହାରିବ ନା sir ସେଟା?
ନା 100% ବାହାରିବ, 100% ବାହାରିବ କେତେବେଳେ ନା ଯେତେବେଳେ when there will be no loss and no byproduct formation or
Sir,
undesired product formation occurs. If a undesired product is formed or any product anything is lost, like as a
sir,
gaseous carbon dioxide, elimination of carbon dioxide, elimination of other molecules, if some amount of the starting material is lost by other method or in other like I told, some of them are lost, some of them are converted to other unwanted products, so then atom economy will not be 100%.
sir. Sir, ଆଉ ଗୋଟେ ସେ physical property of fresh water ରେ tonicity ଟା ଅଛି sir ସେଟା?
Tonicity,
Sir,
tonicity সেটা ସେଇ ତାର ଇଏ ହେଇଥିବ, ମୁଁ କହିଦଉଛି ସେଟା
physical property.
tonicity is the capability of a solution to modify the volume of cells by altering their water content. Tonicity means capacity of a solution to modify the volume of the cells by altering their water content. The movement of water into a cell can lead to hypotonicity or hypertonicity when water molecule moves out of the cell. So basically, if the water molecule moves into the cell, it is called uh, 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 hypertonicity. If it is out of the move into the, it is called hypotonicity. Okay.
Sir,
Okay. Anything else you want to ask?
sir ଏବେ ଯୋଉ ସେ ବେୟର ଲାମ୍ବର୍ଟ ଲ ଟା ପଢେଇଲେ sir,
हाँ,
ସେଥିରେ ମୋଲାର absorbivity ଟା ଟିକେ ବୁଝେଇଦେବେ sir.
molar absorptivity.
Sir, 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 page number 378.
ଗୋଟେ ମିନିଟ୍ ରୁହ, ଟିକେ ଗୋଟେ ମିନିଟ୍ ରୁହ, ଗୋଟେ କଲ୍ ଆସୁଛି। So here, what you want to discuss
Sir, molar
here?
absorbability. Molar absorbability. Page number 3, sir.
3.
7, 8.
So yes, yes, the constant A in this expression is called absorptivity, earlier called as extinction coefficient. This one,
Yes, sir. Yes, sir.
whose value depends on unit of concentration and concentration used, and is a function of wavelength of the monochromatic radiation. The concentration is generally expressed in terms of gram. So this is what is this? This is A. Where is the A? Log. So this, if you derive this Beer log logarithmic law is log I by I0. In I0 in the incident radiation, I is the light which is passes after passing through the passing through the particular particular substance or the cuvette. বুঝলে কি? So that is equal to K prime 2.303 into C. C is the concentration of the analyte inside the cuvette. I0 represents the intensity of incident radiation, I is the intensity of transmitted radiation, and C is the concentration of the substance. So from this, if you derive, come again to log I0 y equal to K into K prime divided by 2.303 into BC. Okay, what is this BC? Where BC, and the rearranging log I0 by I just equal to K prime divided by 2.303 into BC equal to AB into C, where A equal to this constant K prime divided by 2.303. A is the in this equation, A, which is equal to K into K prime divided by 2.303. If you derive this equation, you will find this constant. This A is called molar absorptivity, or called as extinction coefficient, the value whose value depends on unit of concentration and used in a function of wavelength of the monochromatic radiation. The concentration, so this is basically a constant.
Yes, sir.
Okay.
Yes. Thank you, sir.
Okay, ठीक अछि. So should I stop now? Okay, thank you all for listening to me. So stop sharing.